Okay, thank you very much for being here today, and welcome everyone. Before we start to deep dive into today's topic, I would like to tell you a little story. Nico, engineering manager at a top tech company here in Spain, he had a meeting next day with senior management team. So we pre-booked a taxi with Free Now, and he pre-booked it to 6 a.m. next day, so he could catch his flight. However, when he left home and was waiting for the cab, he realized that the taxi driver canceled him. He kept trying to get a new taxi driver, but the application was just crashing and crashing, and he couldn't do anything. At the end of the day, he could grab a taxi, but it was already too late for him. He missed his flight. At the same time, people from the engineering team on Free Now, they wake up with a pager, and after debugging couple of minutes, they realized that the voucher service, the service that provides discounts in our application, it was down. Next day, the data team, they ran some data, and they realized that during the outage, the company had lost 100k euros. And this is the story that I would like to start today to set the ground. This is what inspired me to talk about resiliency for microservices and distributed systems. It can be your e-hailing application, it can be your e-commerce shop on Black Friday, it can be anything, it can be more or less critical. In this case, one person missed his flight. In your case, it can be something more critical, life and death situations, or just losing revenue for your company. Bit story about me. I'm João. I'm Portuguese. I'm a software engineer. I've been a software engineer for 5 years now. Most of my career have taken place in Barcelona, Spain. I love distributed systems, and I work for Free Now, formerly known as MyTaxi. And I serve there as a tech lead / engineering manager, which means that in more or less 2 years, I won't be able to talk about technical things anymore. And just to warm up a bit, how many of you run microservices in production? Okay, quite a few, most of you. How many of you run more than 300 microservices in production? Okay, almost no one. So this is the ecosystem where we live in. We are 3 tech hubs, Berlin, Barcelona, and Hamburg, and we run more than 300 microservices. Most of them, they are in the JVM. So this talk is mostly focused on the tools regarding the JVM, but they can be extrapolated to anything that you are running in your company. And the thing about microservices for us was that, it was really good technology, but for us it was more about scaling the teams, to make the teams be able to work independently from each other, and to make sure that we weren't stepping on each other's toes. And people ask you, why does an e-hailing application such as MyTaxi have more than 300 microservices? What the hell are you doing? And the thing is that whenever you hail a taxi, there's lots of things happening behind the scenes. Vouchers, calculation of the distance to your driver, discounts, many things that are happening. And they can fail at any time. But the question that we should ask ourselves is, are all of these services that important? If some of them fail, would my customer be affected? Because my customer, mainly they want to go from A to B. Why an outage in the voucher service has an impact on that? And that leads to another question, which is, could we operate at partial failure? Could we still get something, get the app running while other services fail? And that's where resilience comes into place. And resilience is the ability to recover from can be an illness in a human being, can be something it recovers its original shape. So in distributed systems, resilience mainly has 3 parts where it's focused. Graceful degradation, which means that you put in place a fallback or a cached response or something like that. Automatic recovery means that you shouldn't deploy anything new in order to fix the partial outage. And the lowest user impact as possible, meaning that if there's a tiny feature that is failing, it shouldn't just render the whole screen black or white. And then the next question that arises is like, what should we do in order to be resilient? Should we just retry a request? Should we just hide the feature? Provide a static fallback? Provide a cached response? Fall back into another provider? Just fail fast and assume that the customer can't do anything at that moment because it's so critical what's failing that it makes no sense for the user flow to continue? And the answer for this is not clear. And the best advice that I can give is for you to sit down with your business people and ask them, okay, what is really the core of our business? If it fails, we start to lose a massive amount of money, or we start not providing value to our customer. And for sure they will say everything. You ask to one department, yeah, it's the pricing service. You ask to other department, no, it's the ETA to the driver, so the user knows how much time they have between being picked up or not. And therefore, my advice is to try to compare. Like, okay, I know that this is important for you, but if this fails, but the other option is no service at all. And then people start to realize that there are trade-offs involved, and they start to change this mindset. And as a case study, I wanted to present this. So every time that we show an offer to our drivers to pick up a passenger, we show usual information, distance, blah, blah, blah. But we also have some mechanisms to incentivize drivers to pick up a passenger. Why? Because sometimes there's more demand than supply. Therefore, every time that we request a tour, we also have one thing called incentive service, which provides this green card here saying, hey, if you take this trip, I'll pay you €2 tops atop of the journey. The thing is, this is important, right? But it's not critical. We could still move passengers from A to B if this doesn't work. So usually, the first response that we have when dealing with such situations of one of the downstream services failing is, okay, we should just retry the call, and that's it. And we have here a very nice example of a retry. And with this, it's solved, right? We fix the problem, everything's fine, we are making money, everything's good. But it isn't. And it isn't because we were just retrying the call indefinitely. And in this case, if the service that runs the incentives, it was just failing constantly, we were not giving it room to breathe. And therefore, we were just putting more pressure into this downstream service instead of backing off and saying, hey, let you recover, and when you recover, I'll start to ask you again for incentives. Okay, fair enough. We know that retrying indefinitely is not good, so we evolve this and we make it with a maximum amount of attempts. And this is much better, right? We retry 3 times. If we can't get anything back, we just return the offer to the driver without any incentive. So now we are good. So before we weren't, but now we can make sure that the driver can still see the offer. But that is not true. Because even if we just repeat the call 3-5 times the number of retries that we consider, it may create this wave of retries because we are a service that operates at scale, many thousands or millions of requests per second. So every 10 milliseconds, every 30 milliseconds, we are just creating a new wave of requests and not giving this room to the downstream service to breathe. And then there are more iterations on this retry thing. Then people start to think, okay, maybe just the amount of retries is not enough. We need to put some exponential backoff in the retry. So people start retrying the request every 10 milliseconds, then 20 milliseconds, then 50 milliseconds, and stuff like that. But even that is not enough, because as we saw with the retries, even with the exponential backoff, with many requests per second, it's highly, it's likely that some of the retries will be just on time also, because there are many requests. So every 10 milliseconds, every 30 milliseconds, and every 50 milliseconds, you will have this wave of things just calling the downstream service. So okay, my pro tips on the retry pattern is just we limit the retries per request, don't retry indefinitely, then use a randomized jitter together with exponential backoff. Therefore, you avoid this synchronicity of many requests being backed off. Separate retryable from non-retryable operations. For instance, if you receive a HTTP 400 bad request, maybe your request is bad formatted, so it makes no sense to retry it again. So making this distinction also alleviates this problem. Another solution with its pros and cons will also be to use a queue mechanism such as Amazon SQS or RabbitMQ or something alike, with each with other pros and other cons. Okay, and as I said, I mostly work in the JVM. So in the JVM we have Spring Retry, which really helps us to make things right from the beginning. We don't need to write our own retryer. We have one that already comes with all these nuances like exponential backoff, randomizer jitter, all these kind of things. And the great thing about Spring Retry is that it provides also a method whenever we end up with the attempts. We can just log or just send an alert or whatever we feel it's right for our service. If you don't like annotations, Spring Retry also allows you to define a retry template that then you can use with a higher function to do exactly the same. So, resilience, right? It's all about retries. We got it. We just need to retry all the calls. But there's one thing that should be taken into account. Idempotence. And idempotence is just a fancy word to say that if you try to do two operations, the same operation twice, it will have the same result. And a couple of months ago, we had this problem in production. We shipped a nice feature called On the Way, where drivers could get tours while they were on the way to their homes, optimizing their usage of the taxi itself. So we defined a REST API, and we said, okay, we create a resource for this on-the-way trip, and then when the driver gets home, we delete this resource with a RESTful API. Everything was great. And someone decided, okay, if we delete this resource at the end, if the deletion is okay, we just handle a 200 or a 204 or whatever. And if this resource doesn't exist, we throw a 404. Makes sense, right? 404 doesn't exist. Makes sense. The problem was that the client wasn't expecting a 404 to be also considered a success. So everything that was not a 200 was treated as an error, and some drivers, they got stuck in the application and they couldn't do anything. And this might be, you might think, okay, this is kind of trivial and this kind of small issue. But the thing is, if we don't think about these kind of things, bad things happen. Like a driver cannot work for 8 hours, he's losing his revenue. Or if we try to consume a REST API, for instance, for payments, and this API is not idempotent, we may end up charging our client twice or thrice because we didn't realize that the API was not idempotent. Now, I'm not going to talk here if the REST API should return 200 and 404 or always 200. I'm not going to debate that. And I'm not also talking about idempotence as a whole here, but just make sure that whenever you consider retrying operations, you take idempotence into account. Okay, retries are fine. We need to think about different use cases. And now I want to talk about graceful degradation, right? The example here is the same that we've been talking until now. So we have an app which has a dispatch service, which dispatches a tour to a driver, and also an incentive service to give these prizes to drivers or whatever. And what we want is that if the downstream service, in this case incentive, is not working, then we can still run our app. Otherwise, we will ruin the experience for passengers and drivers. And in this case, this would mean something like this. So, ideal scenario, we show the bonus. Not ideal scenario, graceful degradation, we don't show the bonus. Okay, makes sense. But how to achieve this in a real application? And the way we achieve this is using the circuit break pattern. And the circuit break pattern is, it works more or less like a real circuit breaker with a small nuance, which is every time that a request to a downstream service is successful, the circuit is closed, everything is okay. If many calls during a short amount of time fail, so the circuit opens, and every now and then it will try another call to the service to see if the downstream service is already healthy or not. So it keeps it open or it closes the circuit depending on this. And in the JVM, one of the most used alternatives is Netflix Hystrix. It's a library created by Netflix like 7 years ago or something like that. And it allows us to make our applications more fault tolerant and latency aware. It allows for graceful error handling and fallback, and it exports lots of metrics, and we will see later why this point is quite key. However, like I said, this was 7 years ago. Many things happen in the tech world and in the microservices world, and Netflix Hystrix is being superseded by Resilience4j, which has a more functional approach and has basically support. Netflix is not supported anymore, so if you encounter a bug, no one will fix it for you. Also, if you work in other stacks like .NET or anything like, you could run other things like Poly and other kind of technologies that just do this same circuit breaking approach. And using Hystrix is quite easy. You just need to extend the Hystrix command class and implement the run method. They also have a non-blocking alternative, which is Hystrix observable command, but the rest is quite similar. And one thing that's key in these kind of things and key in the way we operate Hystrix are these two lines here. We define what Hystrix calls a command group and a command key, which is basically like the downstream service we are consuming, and the operation we are consuming in these services could be create incentive or get last 10 incentives, these kind of things. And we will see later why this, together with the metrics that Hystrix exports, is key for us. Also, to implement fallbacks is really easy. It's just to override a method in the Hystrix command, and you have a fallback. A fallback can be just return cached response, static response, empty, can be many things. And at free now, one key thing is that every service is defined by an abbreviation. So driver gateway service is DGS, incentive service is INCS, for instance. And the cool thing is that all the operations that we have in the service-to-service communications, they are defined with this pattern: source, destination, operation. And what this allows us is to then find root causes much more easily. We use Grafana to monitor our systems. And in one of the dashboards that we have available for every service is the incoming and outgoing latency and amount of requests. Here, with this source destination pattern, you can have very easily, for instance, all the calls that traverse from driver gateway service to incentive service, but you will get also the calls that go from incentive service to another downstream service. So it's quite easy for you to grasp what's the root cause of the problem. We also have distributed tracing in place, but these dashboards, they allow us to see, for instance, just looking into it, okay, is this service, it's failing completely. It's not just one operation, it's everything. And it makes a lot of sense for us. And then we built more things on top of this, because we realized that these dashboards, they were a bit fragile, because when people start to use them and to create this source destination operation pattern, sometimes they assume that the abbreviation for the service was different, or they assumed, or they just misspelled one letter and you couldn't get these graphs right anymore. So we built this small library that just infers what is the source service, and you just put the destination service as a type safe option here with this library, and you just get the operation. Okay, we talked about retries and we talked about circuit breaking, but that's not all about it. There's more things. For instance, if you have in a service A many calls to service B, C, and D, for sure some of them are more important than others also. And we need to have a way to isolate ones from the others, right? Because otherwise we could spend a lot of CPU and memory and network bandwidth calling a lot one of the services that it's not critical, and then the resources would be exhausted for the services that are really critical. And the ship industry, they solved this a long time ago, because whenever the ships they got water into, they wanted to create some isolation between the parts. So if one of the parts got flooded, not the whole ship would get flooded, so it would not sink. And they call this bulkheads. Actually, as a fun fact, Titanic had bulkheads, but they weren't high enough, so that's why Titanic sunk. And in a distributed system, it would look more or less like this. So you define that some workload, it goes through a thread pool, and you define that other calls would go through others, and you can limit this. So you can say just, okay, I just want maximum 1K requests per second to my service B. And this is also really useful because you may, with this amount of requests, you may also get into trouble your downstream service. You can cause cascading failure without knowing. And this would prevent something like someone forgot and he did an HTTP call inside a for loop and something went wrong, the for loop is infinite or something, and this would save your day. And again, Hystrix, it provides already all the tools that we need to do this isolation, this bulkheading. You can use a thread pool, or you can use a semaphore. Usually the main difference is like with a thread pool, you get more isolation because it's a different thread where the call runs. With a semaphore, it runs in the same thread, which means that you can run more concurrent calls to the downstream service, but it also runs in the same thread where you call the downstream service, which means that you can potentially also create problems in your service. Usually, the way Hystrix is configured is to do isolation via thread pool. If you have lots and lots and lots of calls to your downstream service, maybe you can consider to use semaphore. Another funny story that we had was like a couple of months ago, I think. One of our services, it provided statistics. It got an upgrade on a Thursday, a minor version of PostgreSQL or something. And the next day, we realized that something was really wrong. Some queries were taking a lot of time. All that we could see was right. We didn't touch the service. The indexes were okay. We were not actually sure about what was going on, and the service was just keep getting 500. We had circuit breaker in place, so it was not that big issue. But we knew that the service was failing, and we knew that we would need take time to get it back healthy again. So wouldn't it be awesome if we could just ignore some HTTP calls to a downstream service and not even trying to reach it at all? And this was exactly what we did. And we apply what's called load shedding. We just said, okay, for this particular command, don't try to get statistics. It's not important for us if the driver doesn't get the statistics now. He won't complain. But please open the circuit and don't try to call driver statistics service. And then we could have the time to recover it and make sure it was working properly, and then disable this again. This was just changing a configuration. No deploy, no redeploy was involved. Friday, we could do it. Okay, so we talked retries, circuit breaker, bulkheading, and load shedding. And we talked a lot about healthiness. healthiness of our services. And another thing that we should take into account when we talk about distributed systems is to make sure that our systems are healthy. They can achieve their purpose. Usually what people do, they create a /health endpoint in their services, and it is called the health endpoint pattern. Fortunately, in the JVM world and for Spring applications, there's already a Spring health actuator that you can just use out of the box, and you can even configure and tune to your own needs. And it's quite easy to do it. For instance, if you have a payment service that highly depends on Stripe, you could just check, okay, is Stripe working? If Stripe is not working, your service is not working. So you could just apply this kind of logic. Be aware of this kind of pattern, because some people, they just think, okay, so my service depends on service A, B, C, and D, so I will just call all A, B, C, and D to get the healthiness of them. And then A, B, C, and D, they will do the same, and this causes a cascade of calls. Make sure that you just create this health endpoint based on the things that you control. So your own database, your own cache, your third-party provider, if that's a condition sine qua non for your service to operate. So, retries, circuit breaker, bulkhead, load shedding, and healthiness endpoints. As a small summary of what we talked here today, we talked about distributed systems and how they fail. We can't rely really on distributed systems. They fail all the time for lots of reasons. Network fails, new services are deployed, you can contain a bug, etc. And if failure is the constant, just embrace it. We can retry. We can do as many retries as we want, as long as they are contained, so it's a limited number. But carefully. Be careful about idempotence. Be careful about exponential backups without jitter, and how these things can bite you in the near future. And resilience. Resilience is a really great safety net, right? It allows us to make sure that our services, even though they may fail a bit, they will still recover and they will still serve our users. But don't fall into the trap that this safety net will save you. Find the root causes of your problems if something is happening too often. Make sure that you monitor it properly and that you can get observability in your service that allows you to pinpoint what is the piece of the puzzle that's creating a problem, and then fix it properly. And then resilience at free now. What were the benefits of implementing all these things? What were the benefits of putting time to teach the teams, hey, you can't just retry indefinitely. Hey, you really need to fine-tune your workload here, because maybe this part of the system is not as important as this one that you are also doing. And the first thing that comes into my mind is that we had way less fires, and we can work in a much better way, because the first thing that people say back to you when you say, hey, a distributed system is not reliable, people say, yeah, but this will fail like 0.1% of the times. And then you make the math and you say, yeah, but 0.1% of the times millions of requests means thousands of failures. If this is an important API, you may get thousands of tickets saying, hey, this customer didn't get this thing, you are not paying your drivers, you are not applying this count to your users, and then you start this snowball of bug fixing, bug hunting, this kind of thing. So better be prepared to fail than because it allows us to have less failures. It also allowed our people, our engineers that are on call, to sleep better at night. And this is quite key for us. We want to provide really good work-life balance. And if things just fail every now and then, people will just get alarm fatigue, and then they won't look into the alarms anymore, and it gets messy. And as I said, we built some tools, we built some things around resilience in our company, but it's a cultural thing. If people know that their service will fail, they will prepare much better their services for the future, and they will start asking questions way before. They will ask their product owner, okay, and how many times you think this feature will be served a day? And they can start to say, okay, this will be quite problematic if we don't scale it properly, or if we don't put some measures into place and these kind of things. And the last one, as I said, Netflix Hystrix is good, it's great, we use it, but unsupported at the moment. So we need to look into the future, and we don't actually know what's the future for us. Maybe we will embrace resilience for J, or maybe we can rely on service mesh like Istio, because we already run our workload in Kubernetes. But then there are trade-offs, because if you rely on Istio, on a service mesh, who defines these thresholds for timeouts? Who defines these kind of things that with Hystrix, they are contained in the application? If we move it to the infrastructure layer, maybe people think that the platform team should be the responsible for it, when it should be more like a service owner responsibility. So we are still evaluating what are the trade-offs here. And yeah, this is all from my side. I'm happy to chat with you afterwards about resilience, and I'm happy to take any question that you have. If you are shy to ask a question in English, you can ask a question in Spanish, and I will just translate it and answer you. Thank you very much for your time. Any questions? No questions. Was that bad? Okay. I take one.
Hi, nice session here. Thank you. Just one question about the bulk heading. How is Hystrix working with that? I mean, if you said that ROM, for example, you said that it's only handling 10 requests per minute or per second, and your load in production is a lot bigger, how it's dealing with that? Everything is stuck in there, or it's everything timing out? Okay. I don't know.
Okay. If you use the thread pool isolation, it just gets rejected thread exception, and it just doesn't pass there. Anything else? Okay. If you want to talk afterwards, I'm here. Thank you very much.